Hello everyone, my name is Johnny Vu and welcome back to another video. Today we're going to be talking about backpropagation, which is the core algorithm that empowers how neural networks learn. Think of it as an engine that drives the intelligence behind many AI systems you see today, whether it be ChatGPT, NotebookLM, or DeepSeek. We will be focusing on understanding what the algorithm is doing without getting lost in complicated formulas. By the end of this video, hopefully you and I will have a clear idea of how neural networks work and adjust themselves according to their performance over time. So now onto backpropagation. What is it really? Let's consider a neural network designed to recognize handwritten digits. The network takes pixel values as an input and aims to output the correct digit. When the network makes a mistake, we need a way to adjust it. Backpropagation is the method for figuring out how to tweak the network's thousands of weights and biases to reduce this error. Imagine the network is a student learning how to identify the digit 2. Initially, its output may be far from the desired result. Backpropagation helps us understand how sensitive the cost function is to each weight and bias. If wiggling one weight causes a big change to the cost, it means the cost function is very sensitive to that weight. For example, let's say you go through the process described and you compute a negative gradient. Then the component associated with that weight on the edge comes out to be around 3.2, while the component associated on the other edge comes out to be 1. The way you would interpret that is that the cost of the function is 32 times more sensitive to the changes in the first weight. Now, let's go back a little bit into weight adjustment and gradient descent. Suppose a particular neuron in the output layer should be more active or lit up to correctly identify a number 2. There are a few ways to make this happen. One of them is to increase the bias of that neuron. Another way is to increase the weights of the connections from the previous layer to have the brightest neurons. And then lastly, we can just adjust the activations from the previous layer. The connections with the brightest neurons from the preceding layer have the biggest effect since those weights are multiplied by larger activation values. The biggest increases to weights, the biggest strengthening of connections happens between neurons, which are the most active, and the ones we wish to become more active. To improve our network, we use gradient descent. The gradient tells you how you need to change all the weights and biases, all these connections, so as to most efficiently decrease the cost. We care about which adjustments give us the most bang for our buck. The magnitude of each component here is telling you how sensitive the cost function is to each weight and bias. Think of it as rolling a ball down a hill. The ball will naturally roll to the lowest point. In our case, the hill is the cost function, and we want to find the set of weights and biases that correspond to the lowest cost. The negative gradient of this cost function tells you how you need to change all the weights and biases so as to most efficiently decrease the cost. What are large language models? Large language models are sophisticated functions predicting the next word in a text. They assign probabilities to all possible next words. Now, how do LLMs work? A large language model is given a prompt and it predicts the next word, repeating this process to generate text. The model selects less likely words randomly to produce more natural sounding output. Despite being deterministic, different answers typically arise due to this randomness. In terms of training large language models, models learn by processing vast amounts of text from the internet. GPT-3, for example, was trained on an amount of text that would take a human over 2,600 years to read nonstop. Training involves refining parameters or weights. Large language models can have hundreds of billions of parameters. An algorithm called backpropagation tweaks parameters to make the model more likely to choose the next correct word. This happens across trillions of examples, improving predictions on both training and unseen data. Training large language models involves mind-boggling computation. It would take over 100 million years to perform all operations involved in training the largest language models, even with 1 billion additions and multiplications per second. The initial training is called pre-training, focusing on auto-completing text. Chatbots undergo reinforcement learning with human feedback to become better AI assistants. Workers flag problematic predictions and corrections adjust the model's parameters. Computation is made possible using GPUs optimized for parallel operations. Transformers process text in parallel, unlike earlier models. Words are associated with lists of numbers encoding their meaning. The attention mechanisms allow these lists to talk to one another and refine their meanings based on context. Feed-forward neural networks provide extra capacity to store their learned patterns. The specific behavior of large language models emerges from how parameters are tuned during training. This makes it challenging to determine why models make specific predictions. Now let's talk about stochastic gradient descent. In reality, calculating the gradient using every single training example is too slow. So we use a trick called stochastic gradient descent. Instead of using all training examples for every step, you randomly shuffle your training data and then divide it into a whole bunch of mini batches. Let's say each one having about 100 training examples. Then you compute a step according to the mini batch. An example of that, if you were to plot the trajectory of your network under a relevant cost surface, it would be a little more like a drunk man stumbling aimlessly down a hill, but taking quick steps rather than a carefully calculating man determining the exact downhill direction of each step before taking a very slow, careful step in that direction. The approach that the drunk man takes significantly speeds up the learning process. This technique is referred to as stochastic gradient descent. Now for some insights. Even with a well-trained network, it doesn't always learn the patterns we expect. As shown in the video made by 3 Blue 1 Brown, a network might successfully classify digits without actually understanding the underlying structures like edges and loops. The network found itself a happy little local minimum that, despite successfully classifying most images, doesn't exactly pick up the patterns we might have hoped for. This highlights that neural networks can be very good at pattern recognition, but may not generalize in the same way that a human would. So what can we conclude from all of this? Backpropagation is a powerful tool, but it's important to remember what it's really doing, which is pretty much tweaking thousands of parameters to minimize its cost function. Backpropagation, at its heart, is about efficiently adjusting a network's parameters to minimize error. It's a clever way of figuring out which tweaks have the most significant impact. Large language models take this concept to an extreme scale, learning from massive datasets to predict and generate human-like text. The network might not learn what you expect. Even with high accuracy, the network's internal representations can be different from human intuition. Ultimately, understanding backpropagation gives you a peek under the hood of modern neural networks, making the seemingly magical world of AI a little more transparent. Thank you.